I can observe the electric field, the third component of the electric field. I can observe that. I can go out and measure. And that's what, or the magnetic field, that's what radar does. I mean, it does observe some component of these fields. And so you can say, if I want to make something cloaked, cloaked means you can't see it. If I want to make something cloaked, I want to make it look like it's just dry air. It's just there's nothing there, it's air. So let's say we have a reference equation that would be Laplacian u plus omega squared u is equal to 0. This could be the reference equation. This could we could think of this as just we could think this as maybe vacuum. We could think this as nothing out there. This is just the equation in vacuum, or in whatever space you are thinking about. Space without any object in it. And what I'm going to try to do is I'm going to try to, and we know that if there is some object out there, I'm solving an equation with this, like this, where A and Q depend on the object. And what I'm going to try to do is I'm going to try to construct something so that this solution, and we can say, maybe I should call this U tilde, the solution that I measure and the solution corresponding to vacuum, they look the same. Or they are the same where they are observed. And typically where they are observed, I mean, you're not permitted to go and touch the object. You're in what's called the far field. So if you're a little bit away from the object, I'm going to make it such that this solution and this solution are identical or very close. And if I can do that, you cannot observe what these parameters are away from that. So that's the idea of cloaking. That's the idea of cloaking. So let me actually simplify matters quite a bit. And so let me just, and then I'll go to the slides. But let me simplify matters a lot, and let me assume we are at 0 frequency. So for the moment, this is a frequency. So let's assume we are at 0 frequency. So at omega is equal to 0. So at omega is equal to 0, the index of refraction doesn't matter, it drops out. And so you have this equation, divergence A grad U tilde is equal to 0. And you have this equation down here, you have the Laplacian of U is equal to 0. Those are the two equations. So now, of course, what I have to give you is I have to give you a domain. So this is a domain omega. Okay, this is my domain omega. And my fields, U and U tilde, let's say they are equal to some function out here. U is equal to phi out here. And U tilde is equal to the same phi out there because you have some source. I mean, like in a radar, you have some antenna. This is your boundary data. U is equal to phi out there. That's the given thing. Now, what the way I want to set it up is I want to take a particular part of space. Let's say this ball here. And I want to do it in such a way that there's going to be a thing here and this thing here is what I'm going to call the cloak. This is a cloak. I'm going to construct a very special material in there. This is going to be part of A. So A, in this case, is going to look like, so we can say, let's call this region here, this is omega. This thing here is, let's say this domain here is D. And this thing here is, well, actually, let's say this is a ball of radius 2. And this is a ball of radius 1. So just two concentric balls, just for illustrative purposes. And I'm going to make A so that it's equal to what I call the cloak in B2 minus B1. So it's a very special construction I'm going to make of A, of that coefficient. Then A is going to be equal to 1 outside, so in omega minus B2. So that's out here, it's going to be equal to 1. Just like the A is here. This corresponds to A is equal to 1. So it's like air up there. So this is where there's just air. This is where there's a code I'm going to construct. And then I'm going to permit you to put anything you want inside here. So I'm going to make it A, where this is in B1, and this A here is completely arbitrary. You pick it. Your worst enemy picks it. It's completely arbitrary. It can be anything you like. Positive. I mean, let's say we make it so that it's an elliptic equation, so it's positive, definite, L infinity. So it's bounded, measurably bounded away from 0. So let's say I'm going to make A greater than or equal to 1 over lambda, or less than or equal to lambda. Something like this, right? That's what I'm going to pick. Then I can solve this equation with this boundary. Now I have a solution. I have a well-posed problem with that, and the cloak will be also of that nature. It's going to be positive definite. It's going to be, I'm going to make sure that this is an elliptic equation, or almost elliptic. That's one of the questions. But I'm going to make it almost elliptic. And so this thing here, with u tilde is equal to phi, has a solution. It's a well-posed problem. Now you solve the other problem here, which is, so this is u tilde is equal to phi, and this is equal to 0, and u is equal to phi, and this is, of course, on the boundary. And so this is on the boundary. And now the thing I want to obtain is, I want to have it in such a way such that u is equal to identically u tilde in omega minus B2. That means that if you put an observer out here, this person can observe, this is what I call the far field. The far field is away from B2. That's where observers can observe the solution. And out there, you cannot tell the difference between the solution U, which is a solution to the vacuum solution, and the solution with the object you have put in here, and with this particular cloak I have constructed. You can't tell the difference out here. Of course, in here, they're going to be vastly different. But you cannot go all the way down to my cloak and touch it. You can look at it in the far field. And so basically, if I can do this, then I have constructed this object, this part of space, which is surrounded by something, inside which you can put anything you want. And the outside observer cannot see what you're hiding in there, or the fact that you're hiding something. See, it's very easy to hide something. You just put it in a box that's not, that you can't see through. But everyone can see that you put up this box, or this, I mean, the typical way you shield things for electromagnetic waves is a highly conducting boundary condition. So you put it in a metal cage that's highly conducting. But everyone can see that you put up this metal cage, and so they suspect that you're hiding something. They don't know what you're hiding, but you're hiding something. The object here is make it go away so that you hide it, and no one can see that you're hiding it. Then they're not so nearly as suspicious. So that's the idea of cloak. And the idea is that this cloak here will be completely independent of what you have inside. It works for anything. So it's not, you know, there is a stealth technology that they use on airplanes. The stealth technology means you put some kind of absorbing thing on the plane, sort of a foam type thing. Well, they won't tell you exactly what they put, but it's something that absorbs electromagnetic waves. But it's coated on the surface of the airplane. Here you're not coating the particular object. You have done this thing, and that's, you know, the cloak sort of comes from Star Wars and from Harry Potter. You sort of wipe this thing around you, and you are invisible, and the thing you've taken around you is invisible, makes you invisible. You cloak yourself. That's where the thing comes. So maybe, I mean, this is my introduction, and then I'm going to show you how this is done. And actually, I don't want to have this thing here, but I want to have this. I want to have this thing here is approximately equal to utility. So, I mean, I will make them very, I mean, to make them, there are certain, I can do this. But the construction I have to do here is not so desirable. I have to do things that are very single. And I don't like that because engineers don't like it. They say it's hard to construct. I can, on the other hand, I can describe a process whereby you can get them as close as you want. And these materials are perfectly nice. Well, if you want them to be very close, they generate in the limit, but it's a sort of a limiting process. And that's actually what I will discuss, how to make them almost the same, and this is what I would call near cloaking. And so that's what I want to discuss. Now, I mean, since we have given me still another hour, so maybe I should, are there any questions? Because then maybe this is the right, because this is sort of the concept. And so,
that's what this is the amount of time.
I've eliminated the time. This is a zero frequency, but I can do the same. So actually, the work that I have done with Hoi Min is take this to arbitrary frequency and to take this actually to the full wave equation. And take it to a wave equation where you actually have a more realistic, see the thing is, down here, this is the conductivity. And for metals, it is highly unrealistic to have a conductivity that doesn't depend on frequency. And so you have frequency-dependent conductivity. If you have frequency-dependent conductivity, then that means that if you look in the time domain, this is the kind of thing that goes back to become a local term like ddt. But if you had something that depends on frequency here, you get a non-local term in time when you get like a convolution in time. And so we've analyzed it actually for a wave equation with a non-local time term in time. But I mean, just for what I'm doing right now, the description here is for zero limit, the zero frequency limit, so everything is steady state. That's right. But everything that I do in terms of near cloaking can be done actually in the arbitrary, even in the time domain for the wave equation. And the thing is that this cloak here does not depend on the frequency. And since it doesn't depend on the frequency, you can use this cloak in time domain.